Humanity has always searched for life beyond Earth, across oceans, across continents, and eventually to the planets closest to us. And among them, one world stood out. A planet with valleys, rivers, and the unmistakable signs of water. A place that may not have been so different from Earth. But when we finally arrived, we found a world that had already changed. This is Mars. Mars is often described as the most Earth-like planet in the solar system. It has polar ice caps, seasons, day lengths similar to Earth. A Martian day, called a sol, lasts about 24 hours and 37 minutes. From orbit, Mars appears structured and familiar. But on the surface, the reality is different. The atmosphere is extremely thin, less than 1% of Earth's pressure. It is composed mostly of carbon dioxide. Liquid water cannot remain stable under these conditions. Any exposed water would either freeze or evaporate almost instantly. Mars today is cold, dry, and exposed. But its surface tells a different story. Ancient river channels stretch across its terrain. Deltas, lakebeds, and erosion patterns indicate long-term interaction with liquid water. Mars was not always like this. Multiple missions have confirmed that water once existed on Mars. Orbital imaging shows valley networks carved by flowing liquid. Rover missions have analyzed sedimentary rocks formed in ancient lakes. The rover Perseverance rover is currently exploring Jezero crater, a site believed to have once hosted a river delta. These structures are not random. They follow patterns consistent with long-term water flow. Minerals found on Mars further support this. Clay minerals and sulfates form in the presence of water. Their distribution suggests that water was once widespread, not temporary, not isolated, but stable over long periods. Mars had the key ingredient for life. If Mars once had water, what happened? The answer lies in its atmosphere. Mars is smaller than Earth. Its gravity is weaker. Over time, it lost much of its atmosphere to space. One key factor is the lack of a global magnetic field. Without magnetic protection, solar wind directly interacts with the atmosphere. Charged particles strip away gases gradually. NASA's MAVEN mission has measured this process in real time. Atmospheric loss continues even today. As the atmosphere thinned, surface pressure dropped. Liquid water became unstable. Oceans disappeared. What remained froze into ice or escaped into space. Mars did not simply dry out. It was stripped. Mars is no longer a habitable world, but it may have been. And if life ever emerged there, traces may still exist. Microbial life does not require complex environments. On Earth, microbes survive in extreme conditions. Deep underground, inside rocks, in frozen environments. Mars may still host such life beneath its surface. Current missions focus on detecting biosignatures, organic molecules, chemical patterns, microfossils. The Perseverance rover is collecting samples for future return to Earth. These samples may provide the first direct evidence of past life beyond our planet. Mars is not just a dead world. It is a record, a preserved history of planetary evolution, and possibly of life. Mars is often called the red planet. Its color comes from iron oxide, rust, covering much of its surface. But the defining feature of modern Mars is not just its color. It is dust. Fine, electrostatically active dust particles blanket the planet. They are easily lifted by even weak atmospheric motion. Despite Mars having a thin atmosphere, wind still plays a major role in shaping its surface. Dust is constantly transported across the planet. It settles, accumulates, and is lifted again. Over time, this process smooths terrain, covers rocks, and alters surface visibility. Mars is not geologically active in the same way as Earth, but it is dynamically active through its atmosphere. Dust devils, small rotating columns of air, form regularly. They can stretch hundreds of meters high, moving slowly across the surface. Rovers have captured images of these structures. They leave temporary tracks in the dust, revealing wind patterns. Dust is not just a surface feature. It is part of Mars's climate system. Mars experiences one of the most extreme weather phenomena in the solar system, global dust storms. These storms can grow from small regional disturbances into planet-wide events. They can cover the entire surface of Mars for weeks or even months. During such storms, sunlight is blocked. Surface visibility drops dramatically. Temperatures in the upper atmosphere increase due to absorption of solar radiation by dust particles. At the same time, surface temperatures may decrease slightly due to reduced sunlight. These storms are unpredictable. Their exact triggers are not fully understood. Seasonal changes, solar heating, and atmospheric dynamics all play a role. In 2018, a global dust storm engulfed Mars. It ended the mission of the Opportunity rover, which relied on solar power. With sunlight blocked, its batteries could not recharge. This event demonstrated the power of Martian weather. Mars may appear calm, but its atmosphere can transform rapidly. Despite its dry appearance, Mars contains significant amounts of ice. At both the North and South poles, large ice caps are present. These caps are composed of water ice and carbon dioxide ice. During winter, carbon dioxide from the atmosphere freezes and accumulates at the poles. In summer, it sublimates back into gas. This seasonal cycle drives pressure changes in the atmosphere. The polar regions also contain layered deposits. These layers preserve a record of Mars's climate history. Similar to ice cores on Earth, they store information about past atmospheric conditions. Beneath the surface, additional ice exists. Radar data from orbiting spacecraft has revealed subsurface ice deposits at mid-latitudes. In some regions, this ice lies just below the surface. Mars is not a completely dry world. It is a frozen one. Mars has seasons similar to Earth. Its axial tilt is about 25 degrees, close to Earth's 23.5 degrees. This tilt causes variations in sunlight across the planet during its orbit. However, Mars's orbit is more elliptical than Earth's. This means seasonal intensity varies more significantly. Southern Hemisphere summers are shorter and warmer. Northern Hemisphere summers are longer and milder. These seasonal differences influence atmospheric dynamics. They affect dust storm formation. They drive polar ice cycles. They shape temperature distribution across the planet. Mars is not static. It changes over time, not through oceans or vegetation, but through dust, ice, and sunlight. Mars is the most explored planet beyond Earth. Humanity has sent orbiters, landers, and rovers to study its surface and atmosphere. Each mission builds on the last. Each adds precision to our understanding. Among the most advanced is the Perseverance rover. Launched by NASA, it landed in Jezero Crater, an ancient river delta. Its mission is not only to study the environment, it is to search for signs of past life. Perseverance carries instruments capable of analyzing rock chemistry at microscopic scales. It can detect organic molecules. It can identify mineral structures formed in water. It drills into rocks and stores samples in sealed tubes. These samples are intended for future return to Earth. For the first time, humanity is preparing to bring pieces of another planet back for direct analysis. Mars is no longer observed from a distance. It is being handled, measured, sampled. Mars is not only explored on the ground, it is now explored from the air. The Ingenuity helicopter achieved the first powered flight on another planet. Flying in Mars's thin atmosphere is difficult. The air density is less than 1% of Earth's. To generate lift, Ingenuity's rotors spin much faster than a helicopter on Earth. Each flight demonstrates controlled navigation in an alien environment. This capability changes exploration strategy. Aerial vehicles can scout terrain ahead of rovers. They can reach areas inaccessible from the ground. They provide a new perspective. Mars is no longer just a surface. It is a three-dimensional environment. Humanity is expanding how it explores. One of the most ambitious goals is the Mars Sample Return mission. The idea is simple in concept. Collect samples on Mars. Launch them into orbit. Return them to Earth. In practice, it is one of the most complex engineering challenges ever attempted. Multiple spacecraft must coordinate. A lander, a small launch vehicle, an orbiter, a return capsule. Samples collected by Perseverance will be retrieved and launched from Mars's surface. They will be captured in orbit and transported back to Earth. Once returned, they will be analyzed with instruments far more advanced than those carried by rovers. This will allow precise measurements of chemical composition, isotopic ratios, and possible biosignatures. Mars Sample Return is not just another mission. It is a transition. From remote exploration to direct planetary science, Mars is not just another destination. It is a reference point. A planet that once may have been habitable. A world that lost its atmosphere. A system that changed over time. Understanding Mars helps answer fundamental questions. How do planets evolve? What makes a planet habitable? How long can habitable conditions last? Mars provides a comparison to Earth. It shows what can happen when protective systems fail, when magnetic fields disappear, when atmospheres are lost. It is also a target for future human exploration. Plans for crewed missions are being developed. Mars may become the first planet humans set foot on beyond Earth. But before that happens, understanding is essential. Mars is not just a destination. It is a lesson, a record of planetary change, and possibly a record of life beyond Earth.